Hello students, in today's lesson we're going to talk about electrochemical cell and electrochemistry. So as we already discussed, there are two types of cells that we discuss under electrochemistry, that is galvanic cell and the electrolytic cell. As you can see in this diagram, here the energy released, that means here spontaneous reactions takes place, redox reactions. This release the energy. This chemical energy is converted to electrical energy. That means the electron flow creates an electricity, so we can get use of this electricity. But in electrolytic cell, here we supply an external energy source. Because of that energy, we can make a non-spontaneous reaction to occur. Right, so these are the two different types of cells. But in this video, we are going to talk about the galvanic cell, where the chemical energy is converted to electrical energy. Okay, now let's see what happens if we immerse a zinc rod. Let's say this is the zinc rod in a copper 2 plus solution, right? What happens? As we all know, zinc, they will release electrons. That means they will undergo oxidation, and copper 2 plus will accept or gains the electrons. So this is the reaction takes place here. Zinc plus copper 2 plus will give copper solid plus zinc 2 plus, right? So here they will release heat energy. What happens if we separate these two, the zinc rod in a separate compartment and copper 2 plus in a separate compartment? What will happen? So that is called our galvanic cell, right? So here you can see we have immersed a zinc electrode in a solution, zinc solution, and copper electrode in a copper 2 plus solution. Although almost the same redox reaction takes place, we can the energy conversion is different, because we have separated these two systems, so we can make the electron flow out of these metals. So electron flow means, it will create an electricity, so we can use this electricity, right? Okay, so that is called the galvanic cell. We have two electrodes, and they undergo spontaneous reactions, that is redox reactions, and they produce electricity, right? Okay, now let's see what are the terms we need to know under this. So initially we also discussed in our earlier videos, but let's see what are they. Right, as you can see in this diagram, you can see here zinc, it acts as anode, because it has a negative electrode potential value. So we will discuss this, how to find whether it is an anode or cathode. For now, let's say this is the anode, right? So this anode is where the oxidation takes place, right? And the cathode is where the reduction takes place. So in anode, as oxidation takes place, zinc release electrons, and zinc 2 plus is entering into the solution, as you can see in this diagram beautifully, right? So, and in this compartment, reduction occurs, that is the cathode. So here copper 2 plus is deposited, they gain the electron, right? So you can see, as in the diagram here, zinc anode, they get dissolved, and copper cathode, it get deposited, right? So here just a simple tip on or acronym to remember anode and cathode. Anode is where the oxidation takes place. You can remember the acronym.
Ox reduction takes place at cathode, which we can remember as red cat.
So how do we know which is anode and which is cathode, right? If we are given the standard electrode potential value, we can easily say which one is anode and which one is cathode. So let's say we have a we have an electrochemical cell which contains magnesium, they say magnesium and manganese, right? So from this we can see magnesium, they have a minus 2.36 voltage, manganese it is minus 1.18 voltage. So we know, we have discussed, the more negative means they act as anode, less negative cathode. So magnesium is the anode here and manganese is the cathode. Okay, if we talk about manganese and zinc, if we compare these two, manganese, they have the value, standard electrode potential value of minus 1.18 and zinc is minus 0.76. So more negative manganese, zinc is less negative. So it is obvious manganese is the anode and the zinc is the cathode, right?
And if we are given Ag and zinc, right? So zinc, they have the value of negative 0.76, Ag has 0.8, so more negative, that means that is the anode. So zinc is more negative and silver is less negative or positive here, right? Cathode. Let's say we have been given gold and silver, Au and Ag. So Ag, they have the value of 0.8 and Au 1.4, so less positive, more negative, less positive here is the anode. So less positive is Ag, so it is the anode, and Au is the cathode, right?
Okay, so now in this electrochemical cell or the galvanic cell, we'll look at the half reactions that take place. So we have two half cells here, as you can see in this diagram. Let me zoom in. So in your left side, here we have the anode half cell where the oxidation half reaction happens. And in your right side, you have the reduction half cell where the reduction half reaction happens. So you should be able to remember on your left hand side, oxidation half cell, and in your right hand side, it's reduction half cell. So you should you can easily remember as reduction takes place, or reduction half cell is in the right side. So that means R, here R, right? So reduction right side. This is for the half cell, right? Okay, now let's see how do we write the half cell reaction. So at your right hand side, right hand electrode, where the reduction takes place, right? So the reaction there is copper 2 plus 2 electron gives copper solid. And in left hand electrode, which is the anode half cell, oxidation takes place. Okay, in all the cells we discussed, or all the diagrams, you should have noticed a salt bridge across these cell compartments. So what is this salt bridge? Why do we need it? So they have two functions actually. They help to complete the circuit here from this
half cell, that is oxidation half cell to reduction half cell, and they also maintain the electrical neutrality. So what is electrical neutrality? And what is liquid junction potential? Okay, so here in this illustration you can see in your left hand side we have zinc electrode dipped in zinc sulfate solution, and in your right hand side copper electrode dipped in the copper sulfate solution. So if we think about these solutions, let's say in zinc sulfate it says 1m solution. Okay, for illustration let's just assume we have two zinc sulfate molecules. So if we have two zinc sulfate molecules, zinc is a 2 plus ion and sulfate is a 2 minus ion. That means if we take one more molecule of zinc sulfate, it contains 2 plus 2 minus. That means it's electrically neutral, charge is 0. So it's the same case in copper sulfate also, right? So initially these two solutions, their net charge is 0, right? So here net charge is 0, here also net charge is 0 initially. But with time, what happens if we think about the zinc electrode here, their oxidation takes place. That means zinc atoms, they release electrons, and electrons on the surface of the electrode, and the zinc 2 plus ion is released into the solution, right? So let's say only one zinc atom is releasing two electrons, and one zinc 2 plus ion comes into the solution. What happens to the charge in this compartment now? It becomes 2 plus, right? So if we think about the other compartment, here you can see copper is deposited. That means here in this solution we have copper 2 plus from copper sulfate, right? So this copper 2 plus is deposited, so it becomes copper. So they become less positive now. So comparatively they become less positive compared to the zinc, right? So now you can see there is a electrical imbalance in between these two compartments, right? So because of that, the ions will try to move on. So it builds up a potential difference between these two solutions. This is called the liquid junction potential, right? So as you can see here, this is the liquid junction potential. So this creation of liquid junction potential is not healthy for the system to work continuously, because it will lose this neutrality, so there will be electrical imbalance, so the system is unstable, right? Okay, so in order to overcome this liquid junction potential, they have introduced the salt bridge. So you can see here in your zinc compartment, it builds up positive charge. In the copper compartment, it builds up negative charge. So as we have to neutralize these two solutions, here we have introduced the salt bridge. So in the salt bridge, the electrolytes, they are strong electrolytes, and their positive and negative charges are there, so they can release ions into these solutions. For example, in the zinc compartment, as it is positively charged, it can release these nitrate ions, right? So nitrate ions into this compartment in order to balance this, right? Or in order to make this solution electrically neutral. In this copper compartment, you can see here negative charge. So in order to neutralize this solution, they can potassium plus can move into this. So in the salt bridge at the terminals, you can see here there are cotton plugs which will release smooth release of these ions from the salt bridge. And one thing we have to consider, the electrolyte that we use in this salt bridge should not react with the ions in these solutions, and it should, or those should be strong electrolytes as well. Okay, now let's see how do we write the cell notation. So as you can see in here, this is the cell notation of the cell that we used in our lesson today. So you can see initially we write the anode reaction and then the cathode reaction. And you can also see here in anode zinc solid, we have to write down the physical state, and then zinc 2 plus aqueous, and we also have to mention the concentration here. But you can see here in between these two, zinc solid and zinc 2 plus solution, we have a vertical line, single line. This indicates the phase boundary between the solid and the solution, right? So same thing you can note here, this is also the phase boundary, right? In copper also same thing, so solution and the solid, there is a phase boundary, right? So it is indicated by the single vertical line, right? So what is this double vertical line? This shows the salt bridge. And if we do not have a salt bridge, so here we said this is the salt bridge, the double vertical line. Instead of this double vertical line, we should use a single dotted line, right? So it's if there is liquid junction potential. If we have salt bridge, we use double vertical line. That means we don't have liquid junction potential as in here. But if we do not have the salt bridge, that means we have liquid junction potential. This is indicated by this single dotted line between two electrodes, right? And also you can notice when we write cell notation, I said first we have to write the anode reaction. So this is in the order of how the electron flows. So you can see initially zinc, they lose the electrons, they become zinc 2 plus ions. So those lost electrons are gained by this copper 2 plus, and then they become copper solid. So this is how the electron flow happens. So in that way we have to write down the order in the cell notation. In the second example, you can see we have hydrogen gas electrode and Cl2 gas electrode. Hydrogen acts as the anode, and you know we have to have an inert metal. So first the metal is written and its physical state, and the phase boundary is indicated by the single line between solid and H2 gas. And from H2 gas, H plus aqueous, these two phases are separated by this phase boundary single vertical line. And the other half cell, this portion is the oxidation half cells, this is the reduction half cell. So in the reduction half cell, Cl minus aqueous and Cl2 gas is separated by this phase boundary, the single vertical line, and Cl2 gas and the platinum solid, which is an inert metal, it is separated by the single vertical line, the phase boundary. So here we have a salt bridge, so it doesn't have any liquid junction potential. Now let's see what is cell potential and how do we calculate a cell potential. So cell potential is the difference between the electrode potentials. So let's see, let me zoom in this diagram. So here you have zinc and copper. So zinc, they have a negative potential developed and here positive potential developed. So the potential difference between these two electrodes gives the cell potential value. So from this you can see what happens here. So copper, they have the value 0.34 and zinc, they have the electrode potential value plus 0.76, right? So the difference between these two potential gives the cell potential, right? So here in the diagram you might have noticed we have the voltmeter. So if we have the voltmeter, high resistance voltmeter, that means the electron flow or the current is zero, right? So if the current is zero, the voltage we measure between these two electrodes is the maximum voltage, that is called the EMF of the cell, that is electromotive force of the cell, right? EMF. So if we connect a wire instead of a voltmeter, if we connect a bulb, what happens, this EMF gets reduced because they lose the potential, so the value will reduce, right? And you can see here the first reaction is the reduction half cell reaction and the second one is the zinc, that is oxidation half cell reaction. So here's the overall cell reaction. Copper 2 plus zinc gives copper solid and zinc 2 plus solution. And always this overall cell reaction is an exothermic reaction. Now let's see how do we calculate the cell potential. So here zinc and copper, if the standard electrode potentials of these electrodes are given, how do we calculate it? You can see in the diagram in the left hand side we have zinc and in the right hand side we have copper, right? So when we calculate the cell notation, this is the equation we use. E cell is equal to E right minus E left, or E cell is equal to E cathode minus E anode. You know, I said right side reduction happens, that means red cathode is the right side electrode and the other one is the anode, right? Just to remember. So E cell is equal to, when we write down this, we have to write down in the same way, that means the half cell, reduction half cell and the oxidation half cell should be written as reduction, right? E copper 2 plus aqueous becomes copper solid, E zinc 2 plus aqueous becomes zinc solid. So E cell is equal to, for copper 2 plus it is, the value is 0.34 volt and this is the negative value between these two, and for zinc it is negative 0.76, so 0.34 take away negative 0.6 gives us plus 1.10 volts. So this is the cell potential value of the cell we discussed here. So now it's question time. So if you have been given the cell notation as in here, how do you write half cell reactions, or how do you draw the cell diagram? So you should be able to do all those. Let's see how can we draw the cell diagram. Right, so you can see here magnesium 2 plus and copper 2 plus copper. That means you should be able to say the initial portion of this cell notation indicates the oxidation, right? So this is the oxidation half cell, this is the reduction half cell. And you should know, in a cell diagram, from our acronym, if you can remember, red cat, reduction is cathode and reduction is right side, RR, right? So in the right side we will have this copper, so this is copper, and in the left side we have zinc, and also we have the salt bridge, right? Okay, and we can connect this through a wire. Maybe we can put a voltmeter, right? So sometimes they will give you the cell diagrams, and you should be able to predict the cell notation, and you should be able to write the half cell reactions. Hope you can do all these with the explanations, right? Bye for now.